So here we are. It's the image from yesterday from 18 UTC, and you can see the moisture in a layer above approximately 600 hectopascal, and you can see some white areas, some gray scales, and also these black stripes. And I want you to concentrate on these black stripes now for a moment, because as you surely know, these black stripes are a sign for, or can show you the area of jet streams, or more precisely jet streaks. And I want you, as a little warm-up question, to take your pen and show me where you think the jet stream, the jet streak is situated. Just take a pen or take stars and put it to where you think the jet streak is located. Okay, yes, you found one. What about other jet streams, jet streaks? Can you locate some? Nice. Okay, some more, or are you finished? Or tired? Okay. Yeah, thank you. Now we'll take a closer look at the solution, and I will show you the isotax in 300 hectopascal in these yellow isolines. And you see that the jet streak is situated at the moisture gradient from the black stripe to the white cloud. And you all found this jet streak in the rear of the cold front, this one in front of the warm front. This is no jet streak. This is probably a trough axis. We will take a closer look at this a little bit later. Here we have an indication for a jet, but none of you found these two jet streaks. And the reason for this is, okay, there's no black stripe. So you can now say, okay, doesn't work every time. There's a jet streak, but there's no black stripe. And there are many reasons for this. I mean, these jet streaks are situated far up in the north, in the polar regions. And in the polar regions, the black stripes are less distinct, at least if you take geostrophic satellite images, but they are less distinct due to three reasons. The first reason is that the tropopause is much lower in polar regions than in mid-latitudes, because it's colder. And so the moisture gradients may be below the main contribution levels of the water vapor channels. Second reason is that the viewing angle is strongly inclined up there, so the images get a little bit blurred. So the best images for polar regions are probably the images from polar satellites. And last but not least, due to the low temperatures up in the north, the moisture content is much lower than in mid-latitudes. So if we, for example, compare now the real satellite image with the model satellite image, the pseudo-satellite image. So this is the real one. You can see there are much more structures, much more details. And this is the model satellite image. And you can see that the model depicts the jet streaks in form of black stripes, because the model has no viewing angle. So that's always the big difference between the model field and the real satellite image. What more can we see? A nice structure the model was developing over here, some transverse cloud bands in the area of the jet streak, but they don't exist in the real world. But apart from them, the pseudo-satellite image looks really good, really detailed. So we have this bulge over here. You can see here these small and fine water vapor eddies over here. They're also visible in the model satellite image. So the model seems to be really good in that case. But if you ever have the chance to compare the model image to the real image, take a closer look for model errors, for example, for displacements of structures, for differences in the grayscales or different patterns. Then you get a good feeling for the model, or how good the model is on that day. Okay. let's concentrate on the black stripes furthermore. So the black stripes are a sign for the subsiding of dry stratospheric air, as you probably know for sure. And so we can take the black stripes as a measure for the height of the dynamic tropopause. And if the dynamic tropopause is lowered, we know that there has to be a vorticity advection. For example, here you see the height of the dynamic tropopause. You see it as low as 700 hectopascal over here, so really low. And as the PV has to be constant, and the PV is the sum of static stability and absolute vorticity, and when the stratospheric air subsides, the stability decreases, so the absolute vorticity has to increase. And so this is the reason why this region is of interest for every meteorologist for the further development, because this area might be prone to further cyclogenesis or even rapid cyclogenesis. And if we now take a look at the situation at 0 UTC, so 6 hours later, we see that this frontal system has developed even more. We see now a nicer cloud structure at the occlusion. So yeah, always take a close look at the black stripes. Okay, we will still stay at the water vapor image. This time we have the equivalent thickness model field overlaid, and I want you to concentrate on this area, on this thickness rich area. So you see some distinct bright white cloud spots over here, and those are convective cells. And most of you probably know that we need 3 ingredients for convection. The first is moisture. I mean, we are here over the Mediterranean Sea, so there should be moisture. We see that the air mass is really moist and mild due to the thickness rich. What more do we need for convection? Moisture is the first thing. Then we need instability. And if you think about it, we have here the still very warm Mediterranean Sea, and in mid to upper layers it's more cold because of the season, and so we have very steep lapse rates over the Mediterranean area. So we have moisture, we have instability, and in order to start convection we still need lifting. So let's take a closer look at the geopotential height in 500 hectopascal at the same time step, and you can see not that distinct, but you can see probably there's a trough triggering this convection over here, and there's another trough over here. So if you're a forecaster dealing with this area, you should take a closer look at it, because already the convection has started, but as there's another trough, and we know that the situation is still very likely for thunderstorms or thunder showers, and there's another trough axis. So yeah, one should concentrate on this region. And this is also what the guys of ESTOFAX have done, and have issued a warning for this region. A level 1 warning was issued, and they concentrate on the excessive rain. So I thought, okay, I will take a look at the EMPAF product. You probably all know this product. You can find it at the Nowcasting South homepage, or also at the ePort page, the total precipitable water product. And you can see here in the cloud-free areas at least, the precipitable water, it's a really difficult word, the precipitable water of the area, of the whole layer, and we see that there are values up to 30 millimeters. So if some further convective development will take place in this area, the main danger is for excessive rain. So a lot of things we have learned now from the water vapor images, like the jet streaks, the regions of further cyclonic development, convection. But now I want to go to the more wintry part of this weather briefing. So now you can see the air mass RGB from 0 UTC today, and I want you to take your pointer, your star, whatever, and show me which area do you think, or which area you can see in this image shows you wintry weather conditions. So where can you detect winter weather out of this air mass RGB? So please don't be shy, take your pointer and put it to the region where you think you can see anything related with winter. Okay, some first guesses. I will give you some more seconds. You're at least in the right in the right half of the picture. Getting closer and closer, and thank you very much. I will now tell you the solution. I would like you to concentrate on this area, this greenish area over Russia. You can also see some greenish colors over here, very feeble, but at least you can see them. But I want you to concentrate over here. You see these greenish colors, and if we now zoom a little bit in and overlay it with synop observations, you can see that it's really cold. We have really cold conditions. We have -20. Oh, no, you don't see it very good. You can see -20 over here, over there, -16, -17 degrees. So it's really, really cold in this region. So the question is, why does it appear greenish? Why does the air mass RGB show us green colors? And here's the answer. If we take a closer look at the recipe of the air mass RGB, we can see that on the green beam we have the brightness temperature difference between infrared 9.7 and infrared 10.8. And as you probably know, infrared 9.7 is the ozone channel, so more or less shows us the brightness temperature of the ozone. And the infrared 10.8 channel gives us information about the brightness temperature of the surface. And so if the surface is really cold, like -20, or it's even more pronounced if it's -30 or something like that, then this difference is really small. And we have a green contribution in this area somewhere over here, whereas the red contribution is much lower, as well as also the blue contribution. So the main contribution comes from the green beam, and therefore such frosty conditions, such low surface temperatures appear a little bit greenish in the air mass RGB. You often see this greenish color over Greenland in the winter season, or as here over continental Europe. You just have to look closely because it's not that distinct green color, but you can see it. Okay, so here's the reason why it is that cold over Russia. We have a distinct high pressure system over here, and you know, in the cloud-free nights, a cold pool can form over the continent, and so these low temperatures have formed over this cold pool of air has formed over there. Okay, let's jump to this interesting image, to the dust RGB. It's not a current dust RGB, it's from the 25th of November, so from Tuesday. So when I started preparing this weather briefing, I've taken a closer look at different images. So what can I tell you, what can I show you? And I found this interesting feature over here. It's the river Volga. You can see here it appears in greenish colors, and green in the dust RGB is normally a sign for thin water clouds, like here on the edges of the ochre water clouds. These green water clouds are a sign for thinner water clouds, or over desert areas, green is a sign for thin cirrus. But here we have a river in green colors. So I was thinking, what could it mean? And if we take a closer look at or if we jump to the Middle East and take a closer look at the dust RGB there, we can see that also the northern parts of the Caspian Sea are green. So if we combine the information, we have a green river and a green sea. It's nearly winter, so what will it mean? Yes, it's a sign for frozen water. And the reason for it, you can see here again the recipe, but this time the recipe of the dust RGB. And the brightness temperature of this surface or of the river Volga is about -8, -10 degrees, so it's really cold. So we have nearly no contribution from the blue beam, and we have a low contribution from the red beam, as it's always low for cloud-free areas, and we have a medium to high contribution of the green beam. So again, green color means low temperatures, but this time shows frozen water surfaces. So just keep in mind that green in the air mass RGB, it means cold surfaces, but cold grounds, and in the dust RGB, green colors, apart from cirrus or low water clouds, is a sign for frozen lakes. So green in RGBs is sometimes a sign for really cold conditions. Okay, now we will stay with the dust RGB, but take a look at the actual situation. And you see a really big area covered in these ochre clouds, which means low stratus. So we have a big area covered in low stratus and fog, and you probably still remember the prominent high pressure system over here. So it's the typical pattern in autumn or in winter or in spring, that high pressure doesn't mean sunshine, but it means low stratus, which we can see here in ochre colors. And you can always take the satellite image and compare it to the model field, as we will do here. We have the model field of the low cloud cover, and you probably know model fields have their problems with low cloud cover, especially with low stratus. And you see the model performance is not too bad. I mean, there are some errors. The model has not detected the fog over here or the fog over here, but yeah, more or less one can say it's okay. And so, as we are dealing here with low stratus at the moment, I would like to give the microphone to Andreas Wirth, my colleague in Vienna, who will tell us more about the detection of low stratus with the help of satellite images.
Yeah, thank you very much, Lily. My name is Andreas Wirth. I'm a colleague of Liliane, but I'm not working in Salzburg. I'm located in Vienna. And I want to make an excursion with you to the detection of low clouds. So let's have a look what possibilities we have from satellite images. Of course, you have also the model data, as you have seen before. But how can we detect low clouds from satellite images? So first, we have to differentiate between day and night. We have different methods and different satellite channels, which are best suited for day, and others are better suited for the night situation. So let's start with the day. During the day, I would suggest to use the high-resolution visible image. This seems to be the most appropriate because of its high resolution. As you can see here, I noted it, bright gray shades indicate high clouds or mountain snow, and darker gray shades indicate lower clouds. I will show you an example in the next slide. So, moreover, the cloud tops for low fog patches or low stratus usually is uniform, is smooth, and easy to recognize with the eye. Orographic pattern play a role because they often have the same height or even are bit higher than the cloud fields, and so they are delimiting the cloud fields. And you often see also shadows of higher clouds on lower clouds. There is also a handicap in analyzing low clouds from the high resolution images, because if the surface is snow covered, then sometimes it is really difficult to define exactly where the low cloud stops and the snow is visible in the satellite image. This can be sometimes really a problem. So here you have an example. It's yesterday noon. Low cloud, typical low cloud situation, as it happens quite frequently in winter times. And you see low clouds. So maybe you can use your star, yellow star, and show me where you would suspect low clouds. Yes, fine. There's another. Okay, you are right. There's another low cloud patch here in the middle. I can mark it in with my red pointer here. And yes, you're perfectly right. You see, they are delimited by the Carpathian Mountains. The mountain range is clearly visible here. Makes this corner around here. And this is a clear sign that the clouds are not higher than the mountaintops. This cloud feature here is depicted in darker gray shades and has a very smooth cloud top. So it's quite easy, I think, with a little bit of experience to detect low clouds from the higher resolution visible image. So the next situation shows Austria and southern Germany. And here also you see low cloud patches, and I have told you that on top of the low cloud patches you sometimes see the shadows of higher clouds. Can you depict the shadow? Where do you see shadows of higher clouds on lower clouds? Fine. And also in the south. Yes, perfect. So yeah, you see the different height of the clouds just by seeing some kinds of steps, shadows in the satellite image. I see two clouds, two stars here, which also show shadows from higher clouds, but this time I probably think these are shadows from higher cirrus clouds and not from another cloud which is uniformly opaque and throws a more massive shadow on the lower clouds. So to sum up, here you see the one step, and here's another step of higher clouds on lower clouds. This can be very helpful to see which part of the cloud is higher and which part is lower. So during day, for sure, I wrote here you also can use IR image, infrared image, maybe 10.8, which is the typical window channel which is used by many meteorologists to detect low clouds. In many visualization systems you can put your mouse over the cloud and you get the temperature, and from the temperature you have automatically also an idea of the height of the cloud. But with the present generation of MSG we have the problem of the resolution. We have a less high resolution with 10.8 compared to the high resolution visible image, and this might be cause some problems for small scale fog patches in rivers, river basins, or in valleys, for example. And another drawback of using the infrared image is that high cirrus clouds are obstructing the view to the ground. Compared to high resolution visible image, cirrus is transparent in the visible image, and this is not the case in the infrared image. I will show you an example now. This is also a very recent example. I chose this one because we have a clear view over parts of the Alps, with the high resolution visible image, and you can see here that the fog in the valley is present in some parts here, and the higher, the more brighter white colors are coming from snow, and the darker ones from fog. And also in Switzerland, you see clearly where the fog is in the valleys. So, but if we choose, for example, the infrared image, which could depict us the height of the cloud by its temperature, you will see that, yeah, the view is obstructed by cirrus clouds. This is the case here. We cannot see anymore the lower clouds, the valleys, and also the resolution is not high enough to depict the structure of the mountain valleys. So let's jump to the night. With MSG we have a possibility also to detect fog in the night, fog or low clouds, because of the channel 3.9 micrometer. This channel is sensitive to cloud water phase and droplet size, and what we use during the night is the so-called bispectral method, and it uses the 10.8 and the 3.9 micrometer channel. So by both channels have an output of the temperature, the radiation is transformed to temperature, and you can calculate the temperature difference, and by having the correct scale and the numbers, you can depict low clouds. So usually if you make the temperature difference between those two channels, the temperature difference is somewhat in the range between 0 and 10 degrees temperature difference. And here is an explanation how the technique is working. It's principally based on the fact that the emissivity of water cloud is different in 3.9 and in 10.8. In 3.9 the emissivity is a little bit less, so 0.8 to 0.9 compared to 10.8 or around 11 micrometer, where the emissivity of the water droplets are around 1. So this is a product which uses the bispectral method, and what you can see here is depicted also in the legend. It depicts low clouds, very low clouds in darker orange, and with help of a high resolution model, because from the satellite perspective we will never know if the fog or the stratus really reaches the ground, but if we have some surface observations and surface data, we can calculate the probability to see if the cloud reaches the ground or not. And if the probability is high, means that dew point differences and other parameters are fitting, then it's colored in yellow. But in the background of this analysis are satellite data, and it uses the bispectral method I just explained before. So another interesting RGB is the night microphysics RGB, and you see that it's composed of 3 different channels, red, green and blue, and the green channel uses this bispectral method 10.8 minus 3.9, and you see here is the recipe. It uses exactly the temperature difference which is characteristic for low cloud patches, for fog and low stratus. And let's have a look at such an example. This is also a recent, I think it's even the same image I have shown you before. You have again here the mountain crest of the Carpathian Mountains, and you see the greener the clouds are, the more the green channel is active and the more it contributes. That means you can easily detect low clouds here, for example, here, exactly the regions where you put your yellow star a few slides before. The more the image goes into the red, the higher the clouds are, so you can see it here, more red, and if it's very red, like here for example, then you have very high reaching opaque clouds. Another example, sorry, I jumped too far. I'm missing a slide. I didn't realize it. Okay, it was just another example. As this is my last slide, I just wanted to show you that there is another method apart from the night microphysics. It's called the 24-hour cloud microphysics, and it uses, instead of the 3.9 channel, it uses the 8.7 channel. And this here depicts low clouds also not only during the night but also during the day. Well, the night microphysics, due to this channel, which is different during the day because it has some solar contribution during the day, but in the night 3.9 is perfectly usable to depict low clouds, as you can see it here in green. So if you do the comparison, you can also see a drawback. Personally, I would recommend the night microphysics for detecting low clouds in the night. But there's one big drawback. If the temperatures in the north, as you can see it here in the example, are very cold, minus 20 degrees and below, the night microphysics has some problems. Because due to the 3.9 channel, radiation is so low that the radiometer can hardly detect any difference between the ground and the low cloud patches. In this case, and only in this case, I would recommend the 24-hour cloud microphysics, which clearly depicts the low clouds from the red color, which means clear ground and very cold situation. So that's my part. Thank you very much for listening, and I go back to Lily.
Thank you, Andreas. And now we're nearly at the end of the weather briefing, but as next week the meteorological winter will start, I thought I will give you a short outlook to winter, or show you the seasonal forecast from ECMWF that predicts a too mild winter, at least for most parts of Europe. And the signal for too cold temperatures or too low temperatures is here over the Atlantic, but for most parts of Europe it looks like it will be a too warm winter according to the seasonal forecasts. But seasonal forecasts are very tricky, because you probably know that when the forecasting period is longer than 14 days, not only the atmospheric conditions have to be taken into account, but also the oceans, or more precisely their interaction between atmosphere and ocean. And so that's the problem with it, because there are so many phenomena you have to take into account. I mean, you all know El Niño, so the unusually warm sea surface temperatures across the tropic Pacific, or there are other things like the North Atlantic oscillations that describes the pressure distribution, or more precisely the differences to the normal pressure distribution over the Atlantic, or the quasi-biennial oscillation dealing with high-level winds over the equator. So there are so many indices and so many phenomena, and this year they are somehow all contradicting each other. So seasonal forecasts are not that easy and are really tricky, and I mean, there's a clear sign for a too mild winter in these model fields also. This is the period December, January, February, but also in the period January, February, March, it looks like it will be too mild. But I just wanted to say, you probably all saw these model fields, but my opinion is that I'm happy if my weather forecast for the next 3 to 5 days is correct, and predicting the next month is possible, as we can see here, but it's probably a little bit pretentious. So let's take what the winter brings. Let's talk about it in a spring weather briefing and see whether the model fields were right or not. But yeah, I just like the idea or the thought that the nature is not that predictable in the end, and that these seasonal forecasts are not too right. But yeah, probably I just don't like these pictures as we have it here nowadays in Austria, because it's too warm for real snow, so we just have the snow cannons. So I hope the seasonal weather forecasts are not right for this winter. And yeah, I want to thank you for joining this weather briefing, especially the satellite course in Langen. And as I talked in the beginning about the water vapor image, if you don't know, we have just released a new training module on water vapor images, and I will put the link to the text chat box. So if you have not seen it, I think it's worth taking a look at. So thank you, everyone, and see you at the next weather briefing, which will take part at the 17th of December. Thank you.